Hi, I'm Jay James of Picoyune in Berkeley, California. I'm going to talk today about our plasmonic mercury analyzers for artisanal scale gold mining. We have made a new tool for mercury monitoring that offers drastic improvements to the cost and viability of monitoring mercury in the field. Local communities can use our technology to collect an immediate information to guide progress in removing mercury use in these mining communities. In our investigation into the current state of mercury monitoring in ASM, we found that there's some major gaps. There's limited studies occurring, and most rely on international labs to analyze samples. This has inherent delays and costs and difficult logistics. The feedback we get from stakeholders is that immediate results in the field would have a huge impact for the exposed population. Our technology is built around our patented plasmonic sensor, which is made up of a film of gold nanoparticles. Gold nanoparticles, unlike bulk gold, have a peak absorbance in the visible, shown here in the spectrum around 520 nanometers. Gold also has a unique affinity with mercury, so we'll collect mercury vapor out of the gas stream, and mercury itself is very active plasmonically, so you get large shifts upon absorption onto the gold nanoparticle film. So much so that we can measure less than a single atom of mercury per nanoparticle. This is a technique that we use in commercial systems we already have, and some new tools that we're developing specifically for the ASM users. So in ASM, there's some unique needs. You know, our products, our original product was developed under funding from the NIEHS Superfund Research Program, which got us to develop a new tool that's uniquely portable and able to measure total mercury in soils and waters at contaminated sites. The idea that if you can make measurements in the field, you can inform your sampling and get better results without the delays involved in sending out for laboratory analysis. We've built on this original product for a new design that's even more portable and lower cost, that we think is the breakthrough that really makes the opportunity to expand monitoring in ASM possible. Our tools are affordable, robust, and portable. They're free from interference, and they can measure any sample without reagents, gas cylinders, or waste streams. So in the early days of Picoyune, we joined a thing called the NSF I-Core, which was a program for startups that are technology-based to improve the viability of their business by doing extensive customer discovery. And customer discovery is a process for interviewing users, any stakeholders, in order to inform your ideas that might otherwise be limited from a sort of engineering perspective. So this has been very important to us. We've done hundreds of interviews, including a dozen or so since joining the ASM challenge. This helps us to sort of guide our plan for going to market and development of the technology itself. So the opportunity that we see is to provide primarily to provide our technology to the existing stakeholders. These are NGOs, researchers, and governments, to provide systems to communities and miners in the field, and get the measurements where they aren't occurring, and provide that information where it's most practical, with the overall goal of eventually meeting the goals of the Minamata Convention and the safety and health benefits of removing mercury from artisanal mining. We're very familiar with the existing tools for mercury monitoring, and as you can see, mercury monitoring itself is a well understood challenge. There's a number of standard techniques. If you want to measure liquid and solid samples, your options are direct thermal or other commercial labs that do chemical methods to analyze to free the mercury from the samples for eventual analysis from atomic absorption or atomic fluorescence. You can measure mercury at high levels in solid samples using an XRF, which is about a $35,000 instrument. There's also portable vapor monitors that start down as low as $10,000, go up to about the $30,000 range. They don't offer any field calibration, and they are known to have interferences from volatile organics and water vapor and other things that you are likely to find in any setting where you're also finding mercury vapor. So these are sort of the known drawbacks of the competition for our device. Our monitor has some natural advantages. It's a fraction of the cost to assemble. It's hundreds of times smaller than any existing tool, and it has unmatched selectivity. In fact, our plasmonic sensor operates similarly in, full natural gas mixtures, air, nitrogen, argon. So there's really, we haven't yet found any interfering species with our plasmonic measurement. And again, this is, goes back to the fundamental nature of the affinity for gold and mercury and this strong plasmonic signal that's unique to mercury vapor. Other vapor species aren't noble metals, can't provide the plasmonic response. So then the next steps are we're going to push our development and do pilot studies, try to get some feedback from the stakeholders to make sure we have the right plan, and then do direct sales through US nonprofits and sales reps globally, and use our industrial customers for economy of scale to really bring down the cost of these monitors for their field use. Our plan is to start this year with some ASM projects and then ramp up our sales. It's about maybe a $5 to $10 million market for that we estimate, and including some new applications like field monitoring for blood and urine in people near these mining communities, and also characterizing sites in situ. So there are some potential challenges. There's in some cases, mercury use is obvious, and perhaps monitoring doesn't provide the extra information you would need to make a difference. There's the chance that the market size itself in ASM is limited to the point where it can't support even our lower cost tools. There's, with any development, there's technical risks. There are, we have solutions to all these different challenges, and I mean, this is the nature of new technology development. A lot of cycles and iterations to make sure that you can meet those needs. Again, we really think it is important to include stakeholders and channels for feedback on even at the stage of development for the technology. We have a good track record as a company. We've raised over $2.5 million in R&D funding from the National Science Foundation, Department of Energy, NIH. These are through SBIR grants mostly. We do have a commercial system available called the Runabout, shown here at the International Conference for Mercury as a Global Pollutant in Poland, September 2019. This is, we have already, commercialized plasmonic sensing, and I think we have a good path to major improvements for ASM. We've partnered with Geoscene to include their Geoscene engine, which is a reliable way to collect data in remote areas where wireless tools like a phone can connect to the Bluetooth-enabled device. Even without connectivity at the time, you can upload data to the cloud and analyze data remotely in these very difficult locations. The support from the Grand Challenge is going to be critical in addressing ASM for Picoyune. we need to finish the development of the miniaturized sensor. And then we plan to do 5 international sites for pilot projects. We've already established some willing partners in this process, thanks to the Artisanal Mining Challenge. We want to do personal monitors for the team to make sure that that folks traveling out to these sites aren't getting exposed to dangerous levels unknowingly. And then also biological monitoring for the communities, and environmental monitoring for soil and water at the sites to characterize the spread of contamination and the location of mercury use in these communities. We have a great team, myself, Dr. Crosby, and Dr. Lucas. And we really appreciate your time and attention. And if you would like to contact us for any interest at all around mercury monitoring or questions about starting up, that always happy to talk. Thank you so much.